actually going to be visiting right now.
Yes. For almost a week.
Almost a week, anyway, from Collège de France.
No.
So that was...
No. Institute.
From France.
IHS.
Just from France.
Just from France.
Yeah.
IHS. Okay. There was a Wall Street question. Okay. No, it's a great pleasure to have him speak about Feynman path integrals, a joint work with Cécile David-Moret. And, well, I make it short.
Okay, so this is propaganda for our book, which appeared a few years ago. Functional integration, action, and symmetries, which give you the flavor. So, I mean, Feynman path integral is a very difficult subject for a mathematician. Of course, for a physicist, it's a well-accepted device and very useful. But it's known since the very beginning that there are mathematical difficulties. And I certainly don't claim, together with Cécile in our book, that we have given the finite solution. Finite solution is always a dubious concept. But at least we have tried to make it workable. And our point of view was what we call a semi-axiomatic point of view, which means that we try to describe very as accurately as possible what is permitted to do, what are the tools, what are the formulas, and so on, the concept. But we don't pretend that we have a complete rigor. But I can argue that the notion of rigor is quite relative. Quite relative. Let's say, I will take my comparison with the 18th century. I'm very familiar with the work of Euler, I like it very much. And very often people complain that the work of Euler is not rigorous because he considers divergent series and he has no explicit definition of what it means, convergent or continuous. But when you see that he's able to calculate sum of 1 over n squared with 6 digits, and it's a very, very slowly convergent series as we know, he's able to calculate it with 6 digits, he had a good sense of what is a convergent series, obviously. And in some work, I mean, he was dealing with the harmonic series, sum of 1 over n, and he knows very well that it's not finite, and he uses the symbol delta to manipulate that. But I look carefully at his calculations, they are all correct. Because he knew explicitly that he could do linear combination. Well, it's easy to justify afterwards, but not multiply delta by itself. And so, okay. So, I think we are at the moment in the following position. In the 18th century, people knew the rules of calculus. They were doing explicit and fantastic calculation, but they did not have, they had some integral, some derivation, but they did not know the extent of the functional space to which this applies. So they did not know, well, they knew that in the middle they were in a safe place. But if you approach the border, you can get into difficulty. But they stayed away, and even if they did not have, of course, you will never find the definition of a space which is integrable under such a process. But to me, it seems that we are in the same situation for Feynman path integral. We can use them in a safe place and don't go too far to the borderline. André Weil mentioned that he has this idea of what is axiomatic. Well, it was a secret confession to me that he would not do it in public. So he said, rigor is like, he was in Chicago at the time, a big parking lot in Chicago. We know the area is not so safe, but there is a big pole, big light, you put your car just below. You have little chance to be robbed. But if you go to the sides, where there is shadows and so on, well, you are in the danger to be robbed. But you know in science, what is interesting is to go to the border, not to stay under the big light. Okay. And for him, axiomatic was a big light. Hermann Weil had similar comments. So, I will begin. First of all, there was there is a fairy. There was a fairy tale in Princeton in the 40s, and I will just give you some names. First of all, there was Wheeler, John Wheeler, who was professor at Princeton, and he had the good luck to hire Feynman as a PhD. Feynman was a difficulty. He has not been accepted in Colombia. There were quotas against Jews. He was, with some difficulty, accepted at MIT for undergraduate study, and he moved with Wheeler. And there is a story that sometime in 42, many people left to Los Alamos, and that the man, when Feynman brought his suitcase to the station of Princeton, the man who was there told him, "What? I don't understand. You have many friends who go to this very deserted place called Los Alamos." So I hope there was no Nazi spy in the neighborhood. Okay, so, and so Feynman, of course, Feynman. And well, he has explained about his life so often that I don't have to repeat it. And, but another character was Dyson. And it will come in my description, or this will come in my description, mathematical description. Dyson was a British, and he's still very British. His father was an organ player in some church, some parish.
He was a composer.
Oh,
he was a composer, and he was a head of Winchester.
Okay, so better than I thought.
But probably also plays organ.
Maybe, I mean, I've heard only choral music by him.
Okay, and there is a letter from Dyson to his family where he refers to the new French visitor with Cecilia. Okay, so all these people came very well together, and I don't, of course, it's through Cecilia that I heard many of the story, but it's for lunchtime. So now let's begin. What has in the beginning? So beginnings. 2M. Beginning. So the beginning is Dirac in 1928, just after the breakthrough by Heisenberg, and when it was recognized that there were matrices and so on, and the breakthrough of Dirac was to recognize that the commutation law PQ minus QP is minus IH bar resembled the fact that for the Poisson bracket, PQ is 1, or minus 1, depending on your convention. So, and he said, well, it looks similar. And he said that in some Sunday afternoon, I mean, he thought, well, this reminds me of something called the Poisson bracket. But the library was closed, he had to wait the next day to look at some textbook of classical mechanics and recognize immediately. So, the point is that there is more or less, and it should be better to write it as I over H bar PQ minus 2P is 1. For a while it was supposed that you can just mechanically replace in classical formulas the Poisson bracket by this commutator. It's known that it's contradictory because it's true at the first order in H bar, but not at the second order. And that has been the big debate. So, okay, and that's what, so it gave some method to do the quantization. That means going from a classical mechanical system governed by a Hamiltonian and Poisson bracket to a quantum system. Okay, but then another important step was provided by Schwinger, another character in our story, well-known character in that story, who formulated a variational action principle. So, if you suppose that you represent, I will be more precise in a moment, S, the action of the system, and if you if you look at the amplitude you have an initial state B, a finite state A, and you look at the amplitude such that the square of the modulus of that will represent the probability. Then, if your action depends on parameters, then you apply calculus of variation. So S will become S plus delta S, an infinitely small variation. You know, I'm not ashamed to use infinitely small. Don't tell my master who. Delta, so the corresponding variation for the amplitude is given very simply, first order, by I over H bar E delta S B. So it's important to look at this formula. It just says that you have to average, suppose A is the same as B, so you observe in a certain state. You have delta S average, not a change of action, just average over the system. Okay, that's the basic principle. And out of that, well, you will see that the Feynman path integral follows formally from that. Okay, now I have to explain what do you mean by action in this case. Now basically two cases, particle physics and field physics, particle and fields. The work of Feynman, his thesis, his PhD in Princeton 42, dealt with the particle physics, and I will explain that in a moment. But of course, he dealt that in 42, Feynman. But in 46, at the beginning of renormalization theory, when he was at Yale at the moment, then he realized that by doing for fields what he had done for particles in his thesis, he could make forward make great progress. But also he had to supplement this by Feynman diagrams. The Feynman integrals are not so interesting particularly unless you derive from them the Feynman diagram. But the point is that even if you had a rigorous theory of Feynman path integral or sum over history, when you do the expansion with respect to some parameter, to the coupling constant, nothing guarantees that the series will converge. So it's perturbative. But what I would like to show, to convince you, is that at the perturbative level, the rule we give, which is just, a straightening of the form of what everyone does, provide a good transition from a formal path integral to something, evaluation of integral connected with the Feynman diagram, which is that rigorous, provided you accept the normalization, which is another subject. So, okay. So now, what can I do? What is the action? So we have a particle with mass m, we describe a certain path. So vector x of t, which is a vector in the Euclidean space R3, depending on the time, t, and the velocity is, of course, x dot, velocity, derivative with respect to x. And then the action is, of course, 1/2 in mass, the square of the length of the velocity, minus v of x. And v is a potential. Okay, the point is that in the action you have two parts. And if you want to look at the symmetry, dynamical symmetry, so this is Lagrange, and the action is the integral of m dt from an initial time ti to a final time tf. And this S should be considered as depending on the path. So x is a full path, through a function which, the curve if you want, the curve which a full curve which goes from T I to Tn. So x is a function. It's a function, and that means it's a number depending on the function. And that's the integral. So L should be more precisely written as function of 6 variables, Lx dot, and this should be more precisely S of x. So x is Lx of t dot of tt. Each time you specify a trajectory, whether it's the actual trajectory or not, or a fixture of trajectory, then you can calculate the corresponding action. And the principle, classical principle of action is that ds is 0 compared to that which is Feynman. There is a trigger. So this is, of course, I don't have to repeat it. This is well known in classical mechanics, except that in one of our most famous schools, École Polytechnique in Paris, this is not part of the standard curriculum. And Hamilton equations are unknown to the average student. I've been a professor there and complained many times. Okay. So let's. What do we have? Well, for field theory, what we have is that now we have a field which is a function simplified in x and t, and we use standard notation x0 for ct and x1, x2, x3 for the space coordinates. So I will consider this as a function of f1. Fx in of x is in the Minkowski space is R3 plus 1 of 4 dimensions. So it's a function, the field is a function in this, and now instead of the action will be an integral not over time, but over the whole Minkowski space. And what you have, for instance, what you could have is that you have a gradient, Lagrangian should be the square of the gradient plus a minus, m squared, phi squared, or well, it depends where you put m squared c squared. Often everyone omits c. Okay, so that's the Lagrangian depending on the function in four variables. And what you have, so this is the Lagrangian. And what you do, you integrate over the whole Minkowski space 4 dimension, L of phi of x d for x for any given function phi of x. So, and that's the action S of phi. And
don't you need a time derivative?
No, here I include the 4-dimensional gradient.
Okay, so but then the absolute value doesn't mean it's positive.
You're right. Oh, you're right, perfectly. I should put delta mu, d mu phi. No, it's the square is not a positive derivative, it's a Minkowski square. I should say for this remark. So, okay, so, and then you have, of course, the variational principle that I see will give you the Klein-Gordon equation as we know. Okay, so here we get the classical motion, here we get the Klein-Gordon equation, and that's exactly what we want by variational principle. Now, we are to make the transition between the classical mechanics, either particle or field, to a quantum mechanics. And as we know, there are many methods, and the most classical method is the Schrödinger equation. Schrödinger equation. Schrödinger equation, which was written by Schrödinger, and it has to be admitted that it was a very fortunate guess, but the foundation, not okay. But Schrödinger made this guess approximately at the same time as what you know in 1926. There were 2 or 3 people to invent at the same time various forms of quantum mechanics, but they all agree as we know now. So Schrödinger equation is, of course, as you know, a bar dt of the function psi of t, three-dimensional vector, is minus I squared over 2m delta. This now is a Laplace operator in 3 dimensions, psi of x, and minus plus vx sine x. So that's the Schrödinger equation. You don't have to, you know what it is. Okay, now the point is to study the solution of this. And what is important to make the transition to Feynman is a so-called interaction picture, which is not so relevant when you deal with particles, but which is really relevant when you do quantum theory of field, because it guarantees the invariance of the law automatically. Other approaches do not do it. Okay, so what you have is that in general you have a Schrödinger equation of the type E bar psi is H0 plus V psi of H. The Hamiltonian is the sum of two sub-Hamiltonian, where the first part is minus H squared over 2m delta, and the second part is V. Okay, and then you have, sometimes you have a parameter lambda in V, Kaplan constant. Okay, so we want to solve this equation, and the point is that you first define, so it is known that psi of t, psi at time t will be u of t, psi of time 0. And u of t is an operator which is exponential of minus I over h 0 plus t. So, provided you know how to calculate the exponential of an operator, which is not that easy. But then, in many cases, what you can do, u0 of t is the same, but with v omitted. And that's, of course, a propagator for a free particle or free field. V denotes the interaction of your system, field or particle, with the outside system. Okay, so you have G0 t, which is a free. And then what you do, you replace psi of t by let's say call it psi interaction of t, which is u0 of minus t inverse psi of t of psi. So that means interaction. That means you imagine that psi started with the same initial condition, but was developing according to only H0, the free Hamiltonian, not the interaction. And then it's a simple exercise to write what is the differential equation for this u. So it's minus H psi interaction of t. Now it's equal to v lambda v interaction of t psi of interaction of t.
There's a dt missing.
In the definition of psi interaction, you have u0 and psi 0?
Okay, you start what? No, you start at psi at time t. No, it's not that. Psi at time t. Sorry. Initial what? Psi 0. Psi 0.
No, it should be t. Otherwise, you have to write it.
Should be from psi of t.
Ah, that's yes. Yes, yes. You let evolve psi according to the free motion from time 0 to time t, and you bring it back.
Oh, maybe you want psi 0 there, and then you want
No.
Well,
Maybe I'm confused.
but they can't be the same.
No. You take the full development. You take the full development, and you bring it back at you.
And in the next equation, you forgot to write the time derivative. You want to take the time derivative there. No, on the right.
There's a d by dt.
The last equation.
Oh yes, yeah. I'm sorry. Okay. So the point is that you started with well, you can fix the small details. You started from a differential equation which is time invariant, but which has a method in two parts. Now you can replace it by the differential equation which is varying in time. Now this varying in time, this varying in time, but you get rid of Hg. So it's interaction because only the interaction plays the role. So now the contribution of Dyson exponential, Dyson proves the following. So in general, so if you have a general equation, let's say DTF is ATF, well, DTF of a t is ATF of t. So I write it in operator form, and the solution is obtained as follows: is f of t is a sum from n0 to infinity of an n-fold integral. I will precise it: AT1, ATN, ATN, and initial value 0, and the integral is over the domain where was it? 0 smaller than Tn, smaller, etc., than T1, which is smaller than T. So you have an n-fold integral over a domain, and it's so-called, the point is that the times that you are here are oriented in some way, are arranged in some way. So this is the so-called Feynman's Dyson time order integral, exponential, sorry. Because the trick is to rearrange how to make an exponential of that. Well, you first write exponential of integral from 0 to t, 0 to t as ds. Then you develop this, and then you put a t, which means the following. You first develop it exponential, as usual, sum, 1 factorial, I mean integral a, I'll change the slide here, s1, dsn, ds1, dsn. But now there is no restriction. Every variable goes from 0 to t, independently. And then what you say is that when you apply the t operator, you take this product and you rearrange it in such a way that it's in the following order. The first factor which appears on the left corresponds to the first term S1, to the second one S1, and then you have to assume that 0 is smaller than Sn is smaller than S1. And how you get rid of the 1 factorial? Because you have factorial and possibility of arranging a set of n number according to Keswick model. That's just permutation. And instead of, and then at least you can say, instead of integrating in n equal to integrating over a square, you divide the square into 2 triangles. Okay. That's it. And so that's it. But then it was the way the dubious method of Feynman were reformulated in a rigorous way by Dyson. And this formula is a fantastic formula. Of course, it was not long before, but it has. Now, of course, everyone uses it. In combinatorics especially, it's very, very useful. So now what comes after that?
Do you need to say what V interaction of T is over there?
Yes, it has to be, well,